Problem number 4. W is the box with these bounds right here. F is this vector field. We want to evaluate the integral, I should say the flux of F over the boundary of W here using the divergence theorem. Of course, this is a rectangular box. We could do this in a straightforward manner, but then there would be 6 separate vector surface integrals to do. And some of those may be nasty if we look to see that F is a little bit nasty here. Fortunately, we can just convert this to a triple integral of the divergence of F over W itself. What is the divergence of F equal to? Partial derivative of this with respect to x is 3. Partial derivative of this with respect to y is 2y. The partial derivative of this with respect to z is 0 here. And so this is very, very nice. All we have to do is integrate x runs from 0 to 1, y runs from 0 to 2, z runs from 0 to 3, of 3 plus 2y dz dy dx. Okay, so integrating here. Integrating with respect to z here, we just throw in a factor of z times this because there's no z dependence. We plug in 3 and 0. We would just end up 3 times this right there. So 3 times 3 plus 2y will give us 9 plus 6y dy dx. Integrating this with respect to y would give us 9y plus 3y squared. Plug in from 0 to 2. And so this would be 18 plus 3 times 2 squared would be 12. 18 plus 12 is 30. Integral of that will still give us 30. So yeah, we can see just how nice using the divergence theorem makes our life in a situation like this. Okay, that was problem number 4. Let's take a look at problem number 5. So for problem number 5, we have a vector field here. The surface is the part of the plane x plus y plus 2z is equal to 4 in the first octant. X, y, and z are all non-negative. So it is that surface right here. We're told that it's oriented positive third component, so like this here. And so we want to use the divergence theorem to calculate out the flux of F over the surface. So how are we going to go about doing that problem? So what the divergence theorem would tell us is that the flux of F over a closed surface, the boundary of a region W, is equal to the triple integral over W itself of the divergence of F dV. So we have to figure out what is the region that we care about. The region that we care about, this W, is going to be the region that is under, below, inside that plane here, but still in the first octant. So let me call this part S1 here. The boundary of W, the boundary of this tetrahedron, filled in tetrahedron, is going to have 4 sides to this. S1 will be this side. And then S2 will be this side right here. And S3 will be this side. And S4 will be this side. In all of the cases, the orientations here have to be pointing away from the region. So on this side, on the left side, it's pointing to the left. On the back, it's pointing backwards. On the bottom, it's pointing down. So what this is asking for us to do is that instead of calculating out the flux of F over this surface here, S1, we're going to calculate the flux of F over these three surfaces, S2, S3, and S4, and then do this triple integral. And so basically what we can do is that rearranging here, the flux of F over S1 is equal to the triple integral of the divergence here minus the integral over S2 of F dot ds minus the integral over S3 of F dot ds minus the integral over S4 of F dot ds. So we calculate these four integrals, and then we'll be done. Okay, so how do we go about doing this? This might seem a little bit intimidating, but some of these integrals will go very, very, very quickly. First off, let's have the divergence here. The divergence of F is going to be partial derivative of this respect to x is 0 plus the partial derivative of this respect to y is 0 plus the partial derivative of this respect to z is 1. Okay, so we are integrating 1. We're just basically finding the volume of W here. And so the bounds here, let me just fill in. X goes from 0 to 4, y goes from 0 to 4, z goes from 0 to 2. And we take a careful look on here. This here, x goes from 0 to 4, y goes from 0 to 4 minus x. That would be the projection of this tetrahedron down into the xy plane, 0 to 4 minus x. And then z goes from 0 to solve this for solve this for z in terms of x and y. You get 2 minus x halves minus y halves, 1 dz dy dx. And so if you crunch it out, it's not too difficult to crunch this out. I'm just going to write down the final answer at this point. You end up with 16 over 3. And I should say there's actually a clever way to get this if you know a little bit of high school geometry here. The formula for the volume of this tetrahedron, that like this with side lengths 4, 4, and 2, is volume in terms of, volume of like this tetrahedron, where that's A, B, and C, is A, B, C over 6. And if you do 4 times 4 times 2 over 6, you get 16 over 3. Okay, so 1 integral down, 3 more to go, but some of them will start to go very quickly. So the integral over S2 of F dot ds. So let's just observe here, this is pointing the normal vector. The normal vector is pointing in the negative y direction. So it will be -1, 0, -1, 0. And if we do a dot product of this with our vector field, the f dot the normal vector, we'll just get 0. 0 plus 0 plus 0. And so this integral just ends up being 0. If you want to write out an entire parametrization, you could do that, but you will end up with 0. In a similar way, if we take a look at the integral over S3, the normal vector here is pointing in the negative x direction. And so you would probably end up with -1, 0, and 0. And again, if we do a dot product here, we would get 0, 0 plus 0 plus 0. And so this one is also 0. Okay, so that's why I said some of these would go very quickly. These two are just very instantly 0. And so now we're left with parametrizing the base, the bottom of our tetrahedron here. And so we can parametrize that. R of xy is x, y, and 0, because it's characterized by z is equal to 0 there. A normal vector, ry cross rx, will be 0, 0, minus 1. We want it to be pointing downwards away from the tetrahedron. Okay, so then at this point, what do we need to do? F of R of xy will be 0, 0, 0, 0, and z gets replaced by 0 here. So it's just 0, 0, x. And so the dot product here of f with ry cross rx will be 0 plus 0 minus x. When we integrate, so for our integral over S4 of f dot ds, the integral of minus x, and then the bounds here, x will run from 0 to 4, and y will run from 0 to 4 minus x. And I will just write down the final answer here. If you crunch this out, you end up with negative 32 over 3. Okay, so now what do we end up with as our final answer? Well, let's put the pieces together. So the integral over S1 of f dot ds, what we're trying to find is equal to the triple integral of the divergence of f over w, which is 16 over 3, minus, we said this was 0, minus, we said this was 0, minus negative 32 over 3. So 16 over 3 plus 32 over 3 gives you a final answer, 48 over 3, which is 16. So that's how we do this problem using the divergence theorem. Now, let me just to finish off this video do something that's not part of the problem that was assigned, but point out that honestly, it's probably not too bad to do this flux integral here of f over s1 in a straightforward manner. So let me just compute. I'm going to go ahead and verify the divergence theorem here. I probably didn't ask you to do it. I hope it will be instructional. I'm going to compute the flux of f over s1, make sure we get 16 here. So what do we end up with? Parametrizing the surface s1, x, y, and z, solving this for z in terms of x, y, is 2 minus x over 2 minus y over 2. A normal vector to this that's oriented upwards. Minus negative 1/2 is 1/2, minus negative 1/2 is 1/2, and 1. F of r of x, y is 0, 0, and x plus z, 2 minus x over 2 minus y over 2. And when we do a dot product of f with our normal vector, this dot product, this will give us 0 plus 0 plus this, which ends up as 2 plus x over 2 minus y over 2. And if you integrate from x runs from 0 to 4, y runs from 0 to 4 minus x of 2 plus x over 2 minus y over 2, sure enough, you do get 16.